Hey, it's Xavier. I'm going to be solving the other physics problem for extra credit. I'm just going to angle my phone down now because unfortunately I don't have the capabilities to show everything at all. So I hope that's okay. But you know, it's just me doing all the work and writing. So I'm going to tilt my phone down now. All right, here we go. Let's get started. So what we have here is a ball on a string. Well, some sort of mass on a string. So it's kind of like a pendulum. And this pendulum is drawn back. The string on the ball on the string is drawn back a certain amount, then it's released. So it'll go swinging. But then when it reaches the bottom, when it reaches the point where it stops swinging forward and it's about to start swinging backward, at that point it's cut. So this mass on the end of the string, the ball, or whatever mass it is, goes flying because it's cut off. But it had velocity, it had some other stuff, it was moving, but it's cut, so it's no longer going to move backwards. It's going to fly off. What we're looking for here is how far it flies from this point. We're looking for that distance. We want to know how far it goes. And there are a couple ways, there are a couple components to this. We're going to be finding this, which is essentially a projectile motion problem. And for projectile motion, we're going to be using things like the velocity, the time, and the angles that it's going at. So how fast it's going, how long it takes, and at what angle, so we can find out how far it lands. But we also need to know some heights and to figure out the starting velocities. So I quickly drew this diagram larger on this piece of paper, just so it's easier to see and to work with. So first things first, we need to find the heights. So this is the starting point, and this is the point where it's cut at. These are actually two different heights. And this one, they're two different heights. This one should be slightly lower. I just drew it kind of, they were a bit too level, but they are different heights. And we want this height. But luckily we can find this because we have the height over here, the whole height of this whole thing from the top to the floor, which is h. We know the number for, but for now let's just call it h. And we know the angle that this string is at. So we can say, so we know this h, so we can subtract from this h this part to get this. So we can get this part by using some trigonometry. We can use cosine of this angle here and subtract that from this whole h, so we get this part with the cosine, subtracting that from the total h, giving us this part. So we should say h, the big H, the h for this whole height, minus cosine of angle 1, which is theta 1. And we can do the exact same thing for this height here. It's just on a different part. Height 2, we're going to use this theta. It's going to be h2 equals h, the total height, minus cosine of theta 2, that part. So that will give us this height right there. So now what we can do, we can find the velocity. So to find the velocity, we're going to use conservation of energy, according to Newton's laws. So when something has energy on it, it's always going to start and end with the same amount of energy. So it's going to have some amount of energy here, and it's going to have that exact same amount of energy here. So let's take a look at the forces that are contributing to this energy. So here we have mgh. So that is gravity, the g is pulling down on it. That's the force of the Earth. The height, how high up it is here. So mgh1, I suppose. So gravity, the strength of the Earth pulling down, the height is that, and then the mass, so which is m. So that is that force there. The energy it has there is mgh. That is our starting energy. So it should end with that same amount of energy. So let's look at the forces playing on this here. It should have the same amount of energy as this. These have the same energy. So mgh is the energy for this first part. So this will equal the second part. This should also have an mgh because of the same thing, gravity pulling down, a height, albeit a different one, and the mass. So it's also going to be mgh too. But there is a different component. There is the kinetic energy because it just moved. It just went flying through the air, well, swinging through the air. So it's going to have a kinetic energy component. So we're going to add that to it. That component should be 1/2 mass v squared. So that's 1/2 mass v squared because it's the velocity. So this is the kinetic energy, and it's relating to the mass of the object and the velocity that object is going at. So that's that energy factor. So we have these two energy parts right here. It swung here and it's about to swing back, so it still kind of has this here. So it's ending with this energy because that's what it has, yeah, if that made sense. So this is a plus sign. So we can do some algebra to figure out this v here, our velocity. Let's cross out these m's, which is nice. The mass doesn't actually matter on this problem. And then we get gh equals gh plus 1/2 mv squared. We can do some dividing and subtracting, and we essentially get v equals 2gh. It's these different components. h1, that's h1. Oh, h2, my bad. Say h1 and h2. So 2g h1 minus 2g h2. That was just found using some algebra, rearranging this. We subtracted some things and we added some things and all that. That's just algebra. I just skipped some steps to make this go quicker. So that should be, I'm going to fix that parentheses. Sorry about my terrible handwriting. So that should be our velocity. So now we have the velocity at this point. So this is the velocity it's going here, and at this point it's cut. So how fast it's going at this point is this. We're not going to plug in any numbers yet because we still have some more stuff to do. So now that we know how fast it's going at this point, we have the initial velocity for the projectile motion part. So we know how fast it's going at the start of this arc it's making when it flies through the air. But we need to look closer here because there are some angles here that are also important. Because we have this angle here with theta 2, this is actually the launch angle that it's going at, because this whole thing is a circle, and there are some other rules. I think you can use some trigonometry rules to prove this with triangles. But basically, this thing is a circle, and the tangent line here should be this theta. So this launch angle is the same thing, theta 2. We know this is height 2 here, which we said earlier was h minus cosine of theta 2, our trigonomic functions and our height total. But now we need to find this x distance, because remember, we're looking for this whole distance. But we also need to find this distance first because it's flying this part, but we also need this part. That's easy to find with some more trigonometry. We can just call that, sine theta 2. Well, that is sine theta 2. It's just the sine of this, boop, boop. We use the cosine for this part, and we can use the sine for this part. So we got this angle, and then we got this side with cosine and that side with sine, but this is h minus that. This is, all we're looking for here is this, so all we need to say for that is that it is sine theta. That's a theta there. Let me draw this down here. So we have our pendulum, that's sine theta, and this is h2, and this is our launch angle. And we have our initial velocity, but now we need to figure out some other things, like, so we have our, we need to find the time that it's in the air for. We're going to use some equations for this, some kinematic equations for the projectile motion. Sorry, that was worded weirdly. We're going to use some projectile motion equations. We know this is 0. This is the bottom, which this is the h reference, which equals 0, or y equals 0 here. So this ending point is 0. So to find our time, we're going to use an equation that equals 0 for the y. So we're going to use our, let me center this, our projectile motion equation, y equals 0, which will equal our height 2 here, plus our velocity initial for this part, not the whole thing. Our initial velocity for this projectile motion part we discovered here. So this is the initial velocity for this second part. So our velocity initial, sine theta, this part here, and then t, which is the time that it's in the air for. Then we're also going to account for the strength of gravity pulling it down for that amount of time. So negative 1/2 g, our gravity, t, and that's squared. So this is our projectile motion equation for this situation. There are a couple projectile motion equations. This is the one we need to be using here. Our height for this section, our velocity for the air, our sine, this portion, our time, and gravity. So those are all important factors for projectile motion, and we have all of those. But what we need to do here is rearrange this to find t. Unfortunately, what this is, it's going to be a quadratic equation. That's okay, though. Let's rearrange this. Negative 1/2 gt squared plus VO sine theta t plus h2. That's important. We can use this to find our time. I'm going to plug in later for that. Now, we're going to use some other projectile motion equations to find x. This is all in relation to y. Sorry, this is weird. I just drew things badly. I was meant to box this. There's not a 1 minus there. That's just a negative 1/2 gt. So we've got a y component here. We're also looking for the x, which is what we want, the total distance traveled. We found this part, but now with the projectile motion x, we're solving for this part. So our x final is going to equal our x initial, so this part here. And then now let's take a look at the component for this section. That'll be our initial velocity for this section here, which we discovered again was this, times our cosine this time of theta for that section, t. So this is kind of the x component, that's kind of the y component. So in the y equation, we've got the sine theta. In the x equation, we've got the cosine theta, and then of course multiplied by time. The y equation is a bit more complicated because it has gravity and it has the heights. The x equation is much more simple because we just need this is a plus, we just need the initial x position, the velocity, and the angle. Cosine theta, and then of course the time. So now we have everything to solve this. All we need to do now is plug in our numbers. I'm going to rewrite these three equations, our velocity, our y, and then our x equation, over here to plug in our numbers. So our velocity equation is v equals 2g h1 minus 2g h2. And let's calculate that with our original problem. So in the original problem, it said the mass was 0.72. That doesn't matter. Our height original is, well, the total height is 1.25. We don't need that right now, but we need the degrees. We need the angles for this part because we broke h1 and h2 into two different sections. So we can rewrite this as this. So v equals 2g h1, and we said h1 is total h, so 1.25, the whole height, minus cosine of theta. And cosine theta, and theta 1 in this problem is 31.6 degrees. Cosine theta, 31.6. Then we're going to subtract 2gh here. G and 1.25, but this is h2. So cosine theta 2, which is 14.8. That is given to us. And this is all in there. Now we calculate this. Oh, and our g is gravity, by the way. It's 9.81. So let's account for this real quick. We have 9.81, and then 1.25 minus cosine 31.6 minus 2gh again, so 2g, 9.81, then 1.25 minus cosine 14.8 this time for the theta 2. Close that. We get 1.5. So our velocity here equals 1.5 meters per second. Now we can plug that into our other equation here for the y distance to find t. So we have negative 1/2 gt. That is negative 1/2 9.81 t squared plus velocity initial, which is, sorry, I'm having a hard time fitting this all, 1.5 meters per second times sine theta, 14.8, because that was our launch angle, because it's a circle. This is our launch angle, 14.8, plus our h2, which is this initial height here, which we said was over here, h minus cosine theta 2 plus h minus cosine theta 2. All right, well, which is 14.8. So let me solve this very quick. So let's rearrange this. So negative 4.9 t squared plus 1.5 sine 14.8, 0.383 plus our h, so 1.25 minus cosine 14.8, 0.283. Oh, and this is a t, by the way. We still have that t there. So now this is a quadratic equation. We need to solve this. Fortunately, I just have this programmed into my calculator. So let's do this very quickly. Let me check something real quick though. 9.81. Yeah, 4.9. Anyways, so let's go into so it's a quadratic equation. Let's solve this. Our A is negative 4.9. Our B is 0.383, and our C is 0.283. So now our T is going to be 0.282. It's going this with this one because that's the logical answer, because we want, positive time. It's not going to be negative seconds. So that's our time frame. And now that we have our time, we can plug that into our equation over here, which was our final x equation. So our final x equation was x equals x initial plus velocity initial cosine theta t. Our x initial was this distance here. Let's do that real quick, which was just sine theta 2. So sine theta 2, 14.8. That gives us 0.255. So x equals 0.255 plus our initial velocity, which we found to be 1.5 here, cosine theta, 14.8, because that's our launch angle, times t, which we just found here to be 0.282 seconds. So let's do the math on this very quickly. 1.5 cosine 14.8, 0.282, that's our time. Then we're going to add 0.255. And that gives us 0.66, and this is in meters, by the way, equals 0.66 meters. That is our final distance traveled. So we traveled from here. So we traveled all the way here, but we're looking at from this point to this point. We looked at these heights, looked at some angles, and then our projectile motion problem. And we found it is 0.66 meters per second. No, sorry, that's velocity. It's just meters. That's how fast. That's how far we went. So I'll just say this over here, 0.66 meters. All right. Thank you very much. Thanks for watching. Thank you for taking the time. Thank you very much.